So in this video, we're going to look at another example of doing some steady state analysis here. And the problem is asking us to find basically the steady state voltage V out, basically the voltage across this inductor. Now, of course, there are several ways to do this. Number one thing that bothers people is they see this dependent power supply, but we're not going to let this bother us. In fact, we're going to be able to do this, and what might seem like a messy set of equations, not that it's going to be a pretty set of equations, but I think it's going to turn out to not be too bad. So first, before I even start here, I want to kind of determine what kind of analysis technique I could use. I could make two loops if I wanted to, here, I1 and I2. And then if I did that, V out would be the impedance of the inductor times I1 minus I2. So that's one way I could go about doing it. I could also look at some nodes here. For instance, I could say, well, this is VA. This node here would just be VS. This is ground. And then I have this node here, which is going to be this 5I1. And so we could look at this here, and then we could just say, well, then in this case, V out is just simply VA. So there's several techniques we could use. I'm going to go ahead and use the nodal technique just because we used mesh on the previous example. But you could redo this problem doing two loops, and you should get the same answer. So I'm going to erase my loops for now because I'm not going to do that. I'm going to go ahead and erase this over here for now. Because now that we've kind of decided what analysis technique we're going to use, we need to do the phasor transforms here. So we need to write everything in terms of phasors. So the voltage would, of course, become 2.5 at an angle of 9 degrees. And I'm going to go ahead and again put this in Cartesian coordinates, or I'm sorry, rectangular format. So 2.5 cosine of 9 degrees plus j 2.5 sine of 9 degrees. So let's go ahead and do those computations. So 2.47. Actually, maybe I'll carry this out. Actually, I'll go ahead and write this as 2.469. Carry one more decimal point. Plus j 9 sine function 0.391. So that's going to be this voltage supply here. So it'll be 2.469 plus j 0.391. There. All right, now I need to do the phasor transforms of everything else in this circuit. Well, the resistor, again, is easy. That's just 2 ohms. The inductor, well, impedance of an inductor is j omega L. So the impedance there is going to be j times, well, what's my omega here? If I go to the problem here, remember this is my omega. So this would be j times 10, and then L, of course, is just 1 Henry. So this would be j 10 ohms. Okay, so that's j 10. And then for the capacitor, it would be minus j over omega c. And so this is going to be minus j over omega, which is, again, 10 times 330 millifarads, which is equal to, well, you'd have 10 times 0.33, and then you have the reciprocal of that, which is 0.303. minus J. So this would be minus J 0.303 ohms. Okay, so the next thing I want to do before I start writing equations down is I like to rewrite this independent power supply here in terms of some voltages maybe that we're looking for. And for instance, right here, the current I1 is the current going through this 2 ohm resistor. So I1 is going to be Vs minus Va over 2. And so I'm going to go ahead and say that we have here then that this would be 5 times Vs minus Va over 2, or 2.5 Vs minus Va. And I'm going to go ahead and leave things in terms of Vs right now, just because I don't want to have to constantly be writing this term down. All right, so now let's go ahead and write my node equation here. So I know the voltage here, so there's no point in writing a node equation there. So I'm going to write a node equation right here. So I'm going to do the currents leaving the node, which is the way I always like to do it. And so I have here the current going to the left would be Va minus Vs over 2. The current going down would be just Va minus 0 over J10. And then the current going to the right would be Va minus 2.5 Vs minus Va over negative J 0.303. And that's equal to 0. Now, I'm going to look here for instance. Now, it looks like I have 2 unknowns, but this really, we have just one unknown. We know Vs. Now, I'm not going to plug in for Vs just yet because there's a lot of simplification I'm going to have to do, which could kind of muddy the waters here. Now, I'm going to do something clever here on this term here. Notice that I have a 0.303 in the denominator. Well, look here. When I have this was minus J over 3.3 was equal to minus J 0.303. Oh, so wait a minute. If I have 1 over minus J 0.303, that would be the same thing as saying 3.3 over minus J. And so what I'm going to do is I'm going to rewrite this line as Va minus Vs over 2 plus Va over J10 plus 3.3 times Va minus 2.5 Vs minus Va over minus J equals 0. So my numbers are actually still pretty good here. Let's go ahead and simplify this term here, so I'm not going to do anything else. Because I'd have Va minus 2.5 Va, so I have negative 1.5 Va minus 2.5 Vs, and this is all over minus j. Oh, but wait, look at these negatives. Let's multiply this by the negative. This is equal to 0. What I mean by negative, well look, I could bring this, I could bring this negative and distribute it into both of these things here. So I'd have VA minus VS over 2 plus VA over J10 plus 3.3 times 1.5 VA plus 2.5 VS over J equals 0. Oh, well this is actually now making quite a good amount of progress here. I now just need to multiply through, and if I multiply through by J10, all sorts of things start canceling out for me. Because look what I'd have here. Dividing by 2, well that's just J5 times VA minus VS. J10 and the J10 would cancel, so plus VA. These J's would cancel, and so then I'd have plus 33 times 1.5 VA plus 2.5 VS equals 0. Okay, well let's simplify, keep simplifying here. So multiplying this out, let's multiply everything out. Now I'm going to combine some like terms here. And what I mean by that, well, let's see here. I have a VA plus 49.5 VA. So I'd have 50.5 plus J5 VA. So that gets rid of this term, this term, this term, plus 82.5 minus J5 VS equals 0. Well, now I could go ahead if I wanted to plug in the VS, but I'm going to wait even a little bit longer here. I'm just going to go ahead and solve this for VA. So I subtract the term, so this would become a negative 82.5, and then I'd get a plus J5, because I moved it to the other side of the equation. And so VA is now negative 82.5 plus J5. Let's go ahead and plug in for VS now. VS was what here? 2.469. Plus J.39. And this is all going to be divided by 50.5 plus J5. So yes, there's a lot of complex numbers here now that I got to compute out, but that's where I can use my calculator. So let's go ahead and pull up the calculator again here. So we get rid of that. So we have minus 82.5 plus 5i. Actually, I should put another parenthesis out in front of this. Here, let me start this over here. Because that's the numerator. So, minus 82.5 plus 5i times 2.469 plus 0.391 that's going to be divided by 50.5 plus 5i. Hit enter. And we get, of course, our answer. Which tabbed away from it before I actually saw it. Negative 4.07. And 0.00879, 00879. And I just want to double check, was that a plus? Yes, it was. All right, and so that would be in volts. Now, we're not done because, let's go back here. It wanted V out, and we need to write it in terms of cosine here. So the next thing I really need to do is convert this, and I brought my keyboard back up again here, convert this to polar form. So I'll go ahead and do the computation by hand again, even though you can just go ahead and use your calculator. So the magnitude, V sub m, would be the square root of negative 4.07 squared plus 0.00879 squared. So let's put that into our calculator. So 4.07 squared plus 0.00, and this 879 is not going to really pretty much matter at all. And we still get 4.07. I'm not surprised by that. At an angle of, well, let's identify the quadrant this would be in. This is in quadrant 3. And so if I do, that means theta is equal to the inverse tangent of 0.00879 over negative 4.07 plus 180 degrees. And so we'd have 0.00879 divided by 4.07 negative. And then we do the inverse tangent and then add 180 degrees, which is 179.9 degrees. Which I might just go ahead and round to 180 degrees. So my voltage then is 4.07 at an angle of 180 degrees. So my final answer then for the output is 4.07 cosine. Well, what was my frequency? I believe it was 10. Yep, it was 10. Plus 180 degrees volts. So that's what the output voltage is. So let's take a quick look back at this problem again. So had to do and put everything in phasor format, and then we did a nodal analysis taking care of this dependent supply. And let's again talk about what's important. Notice here, really, if we're going to talk about a critical equation, this is the critical equation. This indicates to me that you understand how to do nodal analysis. Now, is this part important? Yeah, it's algebra. Algebra is important. It's good to be able to solve problems. But let's talk about real life scenario. Real life scenario, we would never do this by hand anyway. We would just have a circuit simulator do it for us. Or if we did do this by hand and get to this point, we'd have, a program do this for us. We wouldn't necessarily solve it by hand. It's still good practice to do because it helps develop those algebra skills, helps develop those critical thinking skills. So we still want to practice it. But again, the key thing to get most of the points on a problem is to be able to come up with this equation right here. Okay? Now that's not to say this is the only correct equation, because we already talked about at the beginning of this problem that there was more than one way to approach it. So, if you did it with the loop analysis instead, you'd have a different set of equations, but there would also be some key equations that would be important to have correct. All right, so that actually wraps us up with steady state analysis here. What we're going to move on to next is doing power and AC. And what we're going to have to do is we're still going to have to do these circuit analysis, but when we get into power and we're talking AC and with complex numbers, it's a little bit more tricky, and that's when we're going to also learn about something called the power factor. But we'll start that in the next module.